process over and over and over. But what you really want to do is you want to go as fast as you can without a capacitor, for the simple fact is you want to put a lot of this radiant energy to the source. process over and over and over. But what you really want to do is you want to go as fast as you can without a capacitor. For the simple fact is you want to put a lot of this radiant energy to the source. repeat this process over and over and over. But what you really want to do is you want to go as fast as you can without a capacitor, for the simple fact is you want to put a lot of this radiant energy into the source. It does little things like that. So we'll get it. You know, whether you're going to string up a long wire, you can without a capacitor. The circuits are nothing special, right? They're very simple. There's no closed loops, okay? There's no closed motor loop. There's no magnetic gaps to adjust. There's nothing, okay? There's basically this one little circuit that fires itself through a magneto action, and you capture that electrostatic moment, you transform that, and you send it to the secondary battery. So you got two ways to do this. You can build it up in a capacitor, catch it, discharge it into the battery, and then you want to repeat this process over and over and over. But what you really want to do is you want to go as fast as you can without a capacitor, for the simple fact is you want to put a lot of this radiant energy to the source. And then you want that battery, which is the secondary source, to translate that for real usable energy, which runs your lights, runs your motors, runs your inverter, you know, allows you to use the tools we have today. So whether you're going to capture this from this one little circuit, or you're going to do it like Moray did it, or Skilling did it, or Gray did it, you know, however you want to think of how you're going to get it. You know, whether you're going to string up a long wire antenna and get it, you know, it's there for the taking. Just requires the correct triggering. The machines that you've taped are prototype experimental machines to capture the radiant energy, to find out exactly what it is, how it works, what we can do with it, what we can't do with it, how much mechanical power we can get out of it without inputting more energy into the machine. And you know, we have to state for the record that it's nothing that's new. It's not anything with this mystical halo around it, right? It's It's not that at all. It's always existed here. It's going to be here forever. But with radiant energy, we don't have any instruments. We can see it. We know it's there. You know, it shocks us. It does little things like that. It, you know, it lights neon bulbs between the earth and plastic. Yeah, I mean, you know, it's very, very obvious that there's some form of energy there from the vacuum, right? That we really don't have instruments to measure, and the only thing that we do have to measure it is this gas indicator that glows. You know, so we know that in a way it's fluid. It's like a gas. And so what we need is something to convert the gas to electrical energy. You know, and we're not talking about a fuel cell here. The battery is the only thing that I've found after 40 years of research that can convert any of this radiant energy for usable power. We had a little trigger signal from this battery over here, and that starts the motor, which we're going to do right now. And if you come around to this side over here, you can see over here, we'll slow it down a little bit. Over here it's magnetically triggered on this side. Come over here. So each time one of these things goes around here, it puts a little trigger signal into these coils. And once we get the trigger signal in there, then what we can do is we can, each time this triggers, you know, turns on and turns off, we can collect the charges that would normally be wasted. And of course they go into these banks over here, these capacitor banks, and then this is a timing mechanism here, which it's timed to be about once every second and a half or so, and makes contact here after we collect the charges. And then these capacitors here are dumped through this electronic switch here, and you can actually see the dump here. You watch it and it'll bounce up when it dumps. So if we slow it down a little bit so you can see it. See, it's bouncing around here. Each time that dumps down, the capacitor bank discharges into this battery. So this battery is going up, and this is basically a 12-watt motor. So it's got a little bit of torque to it here. And basically this is what led us to do the bigger motors and how to collect the charges so that we can recharge the batteries on our other motors. And so then if we look at the principle of the way this one works with charge, discharge, charge, discharge, charge, discharge, we can take it up in models. We can move this up to a much more complex machine. Once you understand the principle of the machine, of how it operates, then you can move to a bigger model, which makes this principle go faster and faster and faster. So now the energy is recoverable real fast. In other words, we want to recover this energy as quickly as possible to the battery. The energy from the vacuum is triggered by the radiant. You see what I'm saying? In other words, when you hit that battery with a radiant energy, the battery takes the energy from the vacuum in the chemical process and converts. I want to repeat. You see it wiggle? Now watch. That's because there's no output hooked up on it. So now what we want to do is we want to take this dead battery And we'll get this thing to go here. See that it changed in tone? Now we're going to tell it to go. And we're going to watch over here. This was a completely dead battery, and you're going to see what's coming over here because now we have told it to charge the hell out of it, see? So see, it's up to 24 volts already. So this was a dead battery, so what we've done is we've increased these pulses now 8 times the amount. Want to repeat this process, and so if we were to just stop this for a second, we don't want to get our hands in there, and we put these lights in series. You don't see, remember we put this in series so that the energy has to flow through these lights to the battery. So now if we look at the battery, see the same voltages there. So that means that the energy, and if you look at the lights very closely, as the battery changes impedance, the lights are starting to light. See, now let me take one of these off so we'll get it down to a level where you can see this. Just by disconnecting one bunch. See? Now this is over the top, this is 8 volts over the top of the battery. Okay, so you see, as this battery lowers its impedance, these lights will get brighter. Okay?
What's causing the impedance to be lower?
The energy that comes from the machine is trying to charge this dead battery, which is driving the sulfation off the plates. So now you're starting to return to a normal battery, see? So after charging this battery, okay, in the short time that we did, we should have some indication right now of current in this battery, and we do. The battery now has energy in it. See? Now if you notice one thing, we didn't have this running all that long on the battery, and the battery now is saying, wait a minute, where did I get this energy? This is a dead battery. Okay, so let's let it run a little bit longer. We expanded the machine, so we made it on a 2-tier level. We wanted to see what if the small wheel was exactly like the big wheel, and it's identical in output. We wanted to make sure that the problem wouldn't be in geometry in the end. Okay, so we built the big one first, ran it, tested it, just like we're doing right now. If you look here of what's coming to that battery, see the pulses? They're faster and faster and faster as the machine goes. Pretty soon it's steady. want to charger charges batteries. It's a little more difficult to charge with a conventional charger. Takes a longer time after that. So there is an alteration that takes place from using this form of energy that takes place in the chemical composition of the cells. And once it's attuned to this way of charging, the battery accepts the radiant charger much faster each time, higher power density output each time. So a 33 amp hour battery might look like a 65 amp hour battery. The difference is radiance, one form of energy, EM as we use today, electromotive force energy, isn't capable of charging this sulfated battery because it sees nothing. It sees an infinite resistance. Okay? Radiant energy doesn't, being that the energy is like 100 times or 200 times what the sulfate see, as this battery lowers its impedance, these lights will get brighter. Okay?
What's causing the impedance to be lowered?
The energy that comes from the machine is trying to charge this dead battery, which is driving the sulfation off the plates. So now you're starting to return to a normal battery, see? So after charging this battery, okay, in the short time that we did, we should have some indication right now of current in this battery, and we do. The battery now has energy in it. See? Now, if you notice one thing, we didn't have this running all that long on the battery, and the battery now is saying, wait a minute, where did I get this energy? This is a dead battery. Okay, so let's let it run a little bit longer. We expanded the machine, so we made it on a 2-tier level. We wanted to see what if the small wheel was exactly like the big wheel, and it's identical in output. We wanted to make sure that the problem wouldn't be in geometry in the end. Okay, so we built the big one first, ran it, tested it, just like we're doing right now. If you look here of what's coming to that battery. See the pulses? They're faster and faster and faster as the machine goes. Pretty soon it's steady. See? That's the energy that's going, that is the spiked energy, or the radiant energy that's hitting the battery. And the battery, being that it's a chemical reaction, can translate that into energy. See, it doesn't make any difference if the battery's been sitting 2 years or 5 years, or what the sulfation is on the battery. This energy doesn't care, it just breaks it up. After a radiant charger charges batteries, it's a little more difficult to charge with a conventional charger. It takes a longer time after that. So there is an alteration that takes place from using this form of energy that takes place in the chemical composition of the cells. You know, and once it's attuned to this way of charging, the battery accepts the radiant charger much faster each time, higher power density output each time. So a 33 amp hour battery might look like a 65 amp hour battery. The difference is radiant's one form of energy, EM as we use today, electromotive force energy, isn't capable of charging this sulfated battery because it sees nothing. It sees an infinite resistance. Okay? Radiant energy doesn't, being that the energy is like 100 times or 200 times what the sulfation process is. Here, you can look at it again. Now it's brighter. See? And it'll keep doing that. The sulfation will come right off the plates, and the battery will become a pretty good battery again. This is a monopole motor, okay? This is a monopole motor, and this is in our US patent, and you can find that on my internet site. And this motor over here is what we termed as the motor generator. Quote, that's what the patent office, and the patent examiner and everybody decided it's a motor generator. So, but this showed us the original process to get to this motor. This is an advancement in what the energy is. And what we found out is when we apply conventional electronics to it, you don't get the same radiant output. So we have to go unconventional with this being, and that's why we call this the monopole. Because you see that it's all the same magnetic forces all around the wheel. It's all north poles. And each one of these is on its own independent circuit. And then they're all collected in the end and sent to the battery continuously. So there's no need to do any capacitor. Here's the example. If you just put this battery to another 12-volt battery, you can only divide the charge between the two batteries. So therefore, you have two lower batteries. But in this thing's case, this 12 volts right here is only to trigger this. What comes out of here is the radiant spike, which is about 4 or 5 times over this battery. See, because now this battery, yeah, in other words, that's charging it with no current, basically. And you can see the battery has charge in it because it's barely flickering. So even if we stop the motor, see, the battery's going to go down to its original voltage. If we start the motor, you can see the pulsing process starts and the lights start to grow brighter. So where is this energy, right? Where's this energy coming from? Well, it's coming from the collapsing magnetic fields, right? Which produce a radiant spike. And see, most engineers would take this circuit and short that out because it's not necessary. So they throw away the radiant. That way, if they throw away the radiant energy and don't capture that radiant energy, what happens to this battery is it just gets depleted. This is your typical monopole motor, okay? You only see one pole here. You see, you don't see a north and south push-pull motor. You see a motor that's totally in attraction here, that's a magneto. So what we have here is a magneto radiant generator, basically. We come in with this magnet, we charge the iron. When the magnet moves away, that discharges, fires the transistor. The transistor then fires the coil. The coil then does a flip-flop, generates a radiant spike, and the diodes collect it. And then it's sent to the battery. The monopole motor self-regulates to the load. It automatically servos itself to the load.
If you were to measure the transient voltage of the spikes,
200, 300, 400 volts. It's all a trigger process of sucking it completely out of the vacuum. Electronics, they short that out. Well, they'd have to filter it out or the devices burn out. We don't want to produce any gas in the battery because then you heat it. What destroys this battery is heat. Pushing a lot of current to it for a short period of time, trying to get the charge there. This process is natural, like nature. Nature takes a certain amount of time to charge its battery. See, you can't cause nature to move faster than what she wants to do. In other words, when you push a lot of current to a battery, you're forcing a chemical process which nature says, I really need this much time. You follow me? So she's going to buck you and she's going to fight you. And she's going to cause heating and gassing and bubbling and loss of electrolyte, which is just killing the battery. You know, where a radiant charger comes in, nothing boils, no gassing, coolness in the battery, and this charger is just going to charge on nature's curve. So as long as you follow those rules, the battery will charge, and the primary battery, you can reverse this process over and over. You can do this with dry cells, you can do this with gel cells, you can do this with, these happen to be gel cells. It could be plugged into the wall and burn 1/3 less. This could be running on a solar panel right now in the sun and performing this process. You see, that way the solar panel doesn't have to boil the battery. You could design it so that it could switch its own batteries and run it until the bearings wear out. This is where the term perpetual motion is not true, see, because something's always going to break. Yeah, so you can't call it perpetual motion. Tesla is absolutely right on the button. You know, Tesla is one that, of course, at that time probably started inventing these strange terms. You know, inventing some term like radiant energy. Okay, what is that, guys? Well, see, Tesla discovers this because the people that were running the DC generators at the powerhouses, threw the switch, the wire glowed, killing the operator, And as soon as the current caught up, the glow went away. That's the energy that we want to capture. That's the radiant energy when the wire glows and then collapses back. Those generators were probably at 20,000 volts. So when they threw the knife switch, now just think of this for a second. There's this big inductance. There's this wire that goes down to the end. You throw the switch at the powerhouse, the voltage is already there. That's the dipole. Well, before the current can get down the wire, this wire is emitting great big gigantic lightning bolts that killed the operators. So they had to damp this out some way. So what I've just told you about the radiant energy is exactly what our engineers do. They kill the dipole. They short out the radiant and just use the current. And of course they measure the power then in watts. I'm the opposite. I say, let's find out where the source came from, how it got there. Let's learn what nature's process is right here, because nature will give you all the watts you want if you transform it. He was studying the gas, the etheric gas, because he said it was a gas. Yes, he knew. He knew because he was a great studier of the experiment. You see, do we really do the experiments today? No. We just build what they tell us to build. We don't do any more experiments. You know, we don't learn from our experiments. We don't learn from the observation. You know, it's already in the book. It's been done. Don't waste your time. Here it is. These are the formulas. Learn them and you'll pass. So what do we do with a skeptic? You present a challenge to the skeptic. You get on there and you invite the skeptic. And you say, look, you come and do this for yourself. They won't. They refuse, you know, and even if they did come and do it, they would still deny it. In the end, they would say, nope, I didn't see that. That really didn't happen. That doesn't work that way. See, it's all programming. You see, and it's also difficulty for the skeptic or the skeptical engineer to design a circuit using radiant energy. They haven't been trained in doing it. And they don't get it. They don't understand it. They refuse to look at it. They're blind. So, if the little kids are taught right from the beginning that this is the way you make this machine, and this is why it works this way, and see, you don't need to do this, and you don't need to do that, and you don't have to have any of these things. And see, you still have mechanical energy, and look, you're doing this for milliamps instead of amps. You know, batteries, right, are going to want to run on nature's timescale. Follow me? Nature's timescale says that the battery has a certain rate of discharge for so many hours. You want to stay within that range. You see, otherwise you're harming the battery. The chemical process is causing heat. Cause heat, that's energy that you can measure that's wasted. You follow me? So, when you present a skeptic this, and you say, look, I'm willing to take your challenge.
I summarize this as the 1 watt challenge, which is, I think, that what it's going to take to move forward for any of us is to have the demonstration device on a standalone self-powered basis continuously generates at least 1 watt excess average output power.
I'll take your 1 watt challenge. But these are the rules. I can run an open loop system. I'm not going to couple it back. In the end, what I'm going to do is I'm going to hand you this item and say, tell me how many amp hours you got out of it now from what you put in. Very simple procedure. It's the same thing as a 1 watt challenge. So we're looking at it this way. If I let the skeptic build a circuit, which he says charges the battery, and of course under conventional means, because they're not going to vary, you know, from the textbook operation of this. They're going to boil the battery, they're going to apply huge amounts of current to the battery. I'm not going to do that. The point is, the skeptics are here to keep you burning the energy so that you have to pay for that energy. The thing is that radiant energy is so simple, it surrounds everything that we do. You know, the plants use it all day long, the trees use it all day long, the earth uses it all day long. I mean, the earth communicates with the earth. You know, there's currents running through the earth. You see, it's just a matter of tapping it to get what you want. And then not killing the dipole. In other words, we don't want to kill the dipole. We don't want the plus and minus to go away. We want this energy to keep flowing. We just want to tap a little bit out of it. We want to use that little bit that we tapped to charge something so that we can run our conventional stuff, which the skeptics have designed, because that's what we have.
I think that eventually we'll be able to power the world with negative energy very cheaply and very cleanly. But it is different to use. Your mind has to think backwards on a lot of things that we were all taught in electronics or in our electrical circuits and in power systems and so forth. Now, the amazing thing about negative energy is one day, today, all of our loads, our motors and things like that, are all designed for positive energy and designed for system losses. One day in the future, when we are using and able to use negative energy, we will use loads that are specifically designed for negative energy, and they will just be another amplifier gain. Maybe the load itself will increase the gain 100 times what you're putting into it and you're paying for on the front end. And if you need not to pay that much, you put a few impedance sections before you get to it. What we're saying is, I'm not saying it can be done right now. I'm saying that just if we considered we could develop this very adequately as we went over a period of time, in the future, we'll be able to take a flashlight battery and power New York City, at least in theory. In the real world, maybe we could take that flashlight battery and power one home. Let's look at something a little more realistic. Well, that would be a marvelous thing, because think of how much coal and oil and all that you would save. So as far as the biosphere is concerned, you could really clean up the biosphere. As far as the economics, all modern economics is based on cheap energy, and we would hope cheap, clean energy. It'll deliver you the cheap, clean energy to have a much higher economy for everybody.
It's our point in the future to not consume. We don't want to consume anything. We want to be able to use the energy but not consume it. You know, and it's not as if we're poking a straw in something and letting the air out of a balloon. So we're not going to shrink the earth, if that's what everybody's thinking. You know, we're not going to tap something or cause harm, you know, that could backfire on us someday. You see, but the other alternative is, let's just continue to do what we're doing. And I guess we all shall find out pretty quickly that we've consumed it all up, you know, when we could have used it. But I have faith. I have faith that maybe the new electrical engineers might have to look at something different, you know, because radiant isn't the same thing. You can charge batteries with it, you can heal with it, you can transmit with it, you can have communications with it. If we could get through the political end, you know, all the politics being played and all the little whitewash games and this game and that game and, you know, the status quo. Yeah, the stuff that if we can get through this, then I think we maybe might have a really bright future. Right. Then you can move to a bigger. You can see over here, we'll slow it down a little. And over and over. But what you really want to do is you want to go as fast as you can without a capacitor, for the simple fact is you want to put a lot of this radiant energy to the source. And then you want that battery, which is the secondary source, to translate that for real usable energy, which runs your lights, runs your motors, runs your inverter, you know, allows you to use the tools we have today. So whether you're going to capture this from this one little circuit, or you're going to do it like Moray did it, or Skilling did it, or Gray did it, you know, however you want to think of how you're going to get it. You know, whether you're going to string up a long wire antenna and get it, you know, it's there for the taking. Just requires the correct triggering. The machines that you've taped are prototype experimental machines to capture the radiant energy, to find out exactly what it is, how it works, what we can do with it, what we can't do with it, how much mechanical power we can get out of it without inputting more energy into the machine. And you know, we have to state for the record that it's nothing that's new. It's not anything with this mystical halo around it, right? It's not that at all. It's always existed here. It's going to be here forever. But with radiant energy, we don't have any instruments. We can see it, we know it's there, It shocks us. It does little things like that. It lights neon bulbs between the earth and plastic. Yeah, it's very, very obvious that there's some form of energy there from the vacuum, right? That we really don't have instruments to measure, and the only thing that we do have to measure it is this gas indicator that glows. So we know that in a way it's fluid. It's like a gas. And so what we need is something to convert the gas to electrical energy. And we're not talking about a fuel cell here. The battery is the only thing that I've found after 40 years of research that can convert any of this radiant energy for usable power. We had a little trigger signal from this battery over here, and that starts the motor, which we're going to do right now. And if you come around to this side over here, you can see over here, we'll slow it down a little bit. Over here it's magnetically triggered on this side. Come over here. So each time one of these things goes around here, it puts a little trigger signal into these coils. And once we get the trigger signal in there, then what we can do is each time this triggers, turns on and turns off, we can collect the charges that would normally be wasted. And of course they go into these banks over here, these capacitor banks, and then this is a timing mechanism here, which it's timed to be about once every second and a half or so, and makes contact here after we collect the charges. And then these capacitors here are dumped through this electronic switch here, and you can actually see the dump here. You watch it and it'll bounce up when it dumps. So if we slow it down a little bit so you can see it. See, it's bouncing around here. Each time that dumps down, the capacitor bank discharges into this battery. So this battery is going up, and this is basically a 12-watt motor. So it's got a little bit of torque to it here. And basically this is what led us to do the bigger motors and how to collect the charges so that we could recharge the batteries on our other motors. And so then if we look at the principle of the way this one works with charge, discharge, charge, discharge, charge, discharge, we can take it up in models. We can move this up to a much more complex machine. Once you understand the principle of the machine, of how it operates, then you can move to a bigger model, which makes this principle go faster and faster and faster. So now the energy is recoverable real fast. In other words, we want to recover this energy as quickly as possible to the battery. The energy from the vacuum is triggered by the radiant. You see what I'm saying? In other words, when you hit that battery with the radiant energy, the battery takes the energy from the vacuum in the chemical process and converts it to something that's usable at a later time. In other words, it's a triggering mechanism. You have to trigger your circuits to produce a radiant spike, and then the radiant spike, when it hits the chemical action, sucks the energy from the vacuum. You know, the term free energy is probably the most misused term in the world. The term that I would use is free radiant energy. You see, you want to make up the radiant energy, and you want to do it for the least amount of power input. So what you want to do is have the circuits translate the normal power into a radiant energy. Then you want to capture the radiant energy. Once you capture the radiant
something exciting. All through my body runs 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 something exciting. But something exciting. How
Eu não vou sair daqui. Eu não vou sair daqui. Hoje eu tô feliz, tô sem nada na cabeça. Eu não vou sair daqui até que amanheça. Hoje eu tô feliz, tô sem nada na cabeça. Eu não vou sair daqui até que amanheça. Hoje eu tô feliz, tô sem nada na cabeça. Eu não vou sair daqui.
Hey, hey, hey.
Yeah. So here you see the left battery getting charged. And now the left battery is flying back into the right battery after the charge is removed.
This is where we all came from. The dreams we have, the love we share. This is what we're waiting for. And in my mind, in my head, this is where we all came from. The dreams we have, the love we share. This is what we're waiting for. And in my mind, and in my mind, and in my mind, and in
I found the music on YouTube then after probably
20-minute search per video, maybe an hour. I'm very picky.
We all came from.
If you hear any tracks you like on any of my videos, it will be listed in the description where I got the audio, links and everything.
This is why we're waiting.
Here you see the right battery, the right coil flying back into the left battery. Go back a little bit. So the right battery is receiving charge now. You can see the switches are closed. The plus and minus on the battery have two switches.
This is why we're waiting.
Now the switch is open, and the coil reverses polarity and flies back into the other battery. And that just repeats. Again, here you see the left coil getting charged. It's not flying back into the battery yet. Not until you see the plus and minus terminals on that battery open up. And the switches on the battery both opened up, plus and minus, as you can see. They're angled to the left. Coil loses its charge, field collapses, and flies back in reverse polarity into the other battery. I have a good archive of videos with this circuit in different modes of explanation. I chose this type of music because it represents more of a, electronic situation. It's electronic music, so. Right now, everything's off. All 4 switches are open. Pretty much the in-between state between one coil getting energized and the other. This is the state in between. The state in between which each coil gets energized individually. So you would close the 2 switches on one of the sources and then open it and then return to this state.
Water, the fire in the sky. Smoke on the water, the fire in the sky. Smoke on the water, the fire in the sky. Smoke on the water, the fire in the sky.
Be right back.
Fire in the sky. In the sky. Fire in the sky. Fire in the sky. Fire in the sky. Fire in the sky.
another switching circuit using a double throw relay. On the top left, points B and C is just a single pole switch, a reed switch. And when the coil to the right of it receives charge in red, it will pull the switch open, or I'm sorry, it will close the switch and send power from B to C. Or it will send connection from B to C, and thereby giving C at the bottom right of the diagram, all the way to the bottom right. See where it says point C? It's just basically connecting the negative. So you're switching the negative. The positive is jump to the power switch. The 12-volt battery at the bottom. To the left is the positive, and to the left of that is the switch to turn on the power. When you turn on the power, it energizes the coil to then turn off the power. Sorry. Right. Yeah, so as soon as you turn this on, it turns itself off. And then it uses a magnetic field to turn itself off. So as soon as it turns itself off, so goes the magnetic field that it was using to keep itself off. So the reed returns back to the normal position of the on, and then it just repeats. So it oscillates like that. It doesn't have a pulse width modulator or nothing. The other circuit that looks similar to this uses a pulse width modulator, so you can vary your frequency. I just created two of these versions. One that pulses itself automatically by disconnecting itself from source, and it uses magnetism to reconnect to source again, so that doesn't require power, and that's how it can turn itself back on. And it becomes a switching circuit that's not variable. Not variable by a knob that controls resistance to a base of a transistor or something, just variable by voltage levels. You can decrease your voltage and that should decrease the speed at which it oscillates. Because the lower the voltage, the longer it takes to disconnect power and generate the EMF field. You need to generate the EMF field by turning the power on, and once that field is generated, it controls the relay at the top left, B and C points. It's a reed. The reed has a magnet on it. So the field that's created on your electromagnet at the very top in red will influence the reed to either turn on or turn off whatever you're trying to do. When you see green in the coil, that's the flyback reverse. The polarity reverses and flies back into the source power battery. Again, you could put batteries in parallel here. So points B and C They just connect the negative to the source, to the whole circuit. Connect or disconnect. In this case, we are energizing the coil to the right of the reed at the top left. In order to disconnect power. You could put a magnet behind the reed to get it to return to its original state of being on. And this is a completely different circuit, but still a flyback circuit, nonetheless. Same function, different switching though. So you have three states in this circuit. State 1 would be the battery on the left giving power to the coil above it. State 2 would be the battery on the right giving coil to the... Man, it's difficult to talk when you hear yourself repeating it. Okay, let me do that again. Okay, I muted myself. The three states this circuit has. State 1, battery to the left is giving energy to the coil above it. Then the next state that the circuit takes is state 2, which looks like that, where you see all 4 switches open. And then state 3 is the right side battery closes like that, energizes the coil above it. Those are the 3 states. Then it goes back to state 1, which is the left side. Well, there's 3 states, but one of the states is repeated twice, and the other 2 states are created once for an entire operation. So you energize the coil on the left with the battery on the left. Then you open up the circuit, and all switches are open. State 2. Then the battery on the right closes the switches to charge the coil above it. That's state 3. And then you go back to state 2 again. All switches open. And then you go to state 1 and you close the switches on the left. And then you go back to state 2. All switches open. Then you go to state 3 and close the switches on the right. Then you go back to state 2, all switches open. And then you go to battery to the left and you close the switches, state 1. Just keeps going back and forth like that. You minimize your current usage and just create a high voltage spike. Place it over the batteries over and over again. Create a high voltage spike without creating any load on these batteries by using a high impedance coil. Yeah, I've been streaming this circuit for more than a year. I'm pretty sure nobody is catching on to it yet, because I'm not getting a lot of questions. But I am feeling like that's about to change soon. I feel like it's going to start making sense real soon to everybody. Gotta put the switching thing behind you. If you don't get it, just forget about it. Just look at the coil and see how it flies back into the other battery. Don't try to focus on how the switching is doing whatever. You know, that'll just confuse you. I mean, heck, I'm the author of this and it confused me. But I promise anyone who embarks on this, just get you running like it's shown here, it will work. You're looking for a switching mechanism for this, it's on my channel. There's a commutator design and a magnetic solenoid method.
ding, ding. Bam, bam.
This may be the track that got me to use this entire hour of audio.
Bam, bam. Ding, ding.
My preferred method of triggering this circuit is with the magnetic controlled solenoid. The two solenoids, one magnet design with double pole, double source. I'm going to edit that into this video here later.
Bam, bam. Ding, ding. Bam, bam.
All you people in the house, get up and scream and shout. Say hey, 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 all you people in the house. Say hey, hey, hey. All you people in the house. Say hey, hey, hey. All you people in the house.
Repeat this process over and over and over. But what you really want to do is you want to go as fast as you can without a capacitor, for the simple fact is you want to put a lot of this radiant energy to the source.
Here you have the magnetically controlled solenoid relay with a double source and a double pole. You would wire one of the relay coils with the coil above the battery. In series. And when that relay coil is energized, so is the coil above the battery, which represents the coil around the wheel, 90 degrees separation, the two coils around the wheel. You can see here in the image.
You transform that back to something that's usable for the
coils,
battery,
90 degrees.
see, which is a radiant DC. And the battery then after that just charges like mad.
This is going to be a fun project. I plan on making that magnet in the middle. Never touch anything but the contacts. It will move at a high RPM, high speed, and there will be a smaller magnet attached to the core, the tip of the core on the solenoid. Small enough, probably a Neo, so that it has the strength to keep the magnet from actually grabbing to the iron. But you'll still have more of the core exposed because you're going to use a small magnet. Let's say the diameter of that core of the trigger coil, the coil that you're using to trigger the circuit. The two coils you see here, those are trigger coils. They're just going to be used to trigger your drive coils, which are two additional coils on the bottom right in the circuit there. You would place one of the trigger coils in series with one of the coils on the bottom right, so that they get powered at the same time. But so imagine your core material on the trigger coil is, let's say the circumference is the size of a penny. You're going to put a magnet, stick it to that iron tip of that core that's the size of a penny. You're going to get another magnet, probably a Neo, and it's going to be the size of, let's say, 1/4 of a penny. That way you still have 3/4 of the iron showing and 1/4 of it is magnet. So you can have 3/4 of iron attracting your center magnet in red and blue there, and the Neo attached or glued to the core is 1/4 the size of a penny, but it's there to just prevent your center magnet in red and blue from smashing into the iron, and it'll just create an air gap. As soon as it gets close enough, it'll stop, because you're going to place that Neo attached to that core in repulsion to whatever side of the reed magnet is facing that Neo magnet attached to that core, so that it repels once it gets close enough. So using a smaller magnet enables you to allow the iron to pull the reed towards the iron, and then also having a smaller magnet glued to the iron. Once your bigger magnet gets closer to that smaller magnet, it will repel and prevent the bigger magnet from smashing into the iron and breaking your magnet. So essentially, it'll never touch the iron, but it'll move towards the iron. When it gets close enough, it'll stop by the use of magnetic fields and repulsion. That's what I plan to do with this. So that's the reed solenoid relay double source, double pole throw that you saw just a second ago. It would run this circuit.
want to repeat this process over and over and over. But what you really want to do is you want to go as fast as you
Do it! Do it! Do it. Do it. Do it. Do it. Do it! Who is doing it? Do it. Do it. All of it. Do it. Come on! Do it now!
Pink Panther is simplicity and identification.
널 위해 사랑면 난 아파도 강한 척할 수가 있어서 사랑이 사랑을 더 완벽하게 늘 모든 적들은 다 숨겨지게 이루어지지 않는 꿈속에서 피할 수 없는 걸 지키면서 I'm sick of this freaking love, freaking love, freaking love. I'm so sorry but it's freaking love, freaking love, freaking love. I wanna be the goat just for you. 세상을 전 just for you. 전부 바꿔서 just for you. 나를 너는 who are you? Hey, 우리만의 너는 없어. 내가 와도 잊어버렸어. 나도 내가 누구였는지도 잘 모르겠다. 떠오르다 뒤걸려봐. 너는 대체 누구? 위해서라면 가슴 더 깊은 척할 수가 있었어. 위해서라면 가슴 더 깊은 척할 수가 있었어. 위해서라면 가슴 더 깊은 척할 수가 있었어.
Do it. 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 Who is doing it? Do it. Do it. All of it. Do it. Come on! Do it now!
Una mattina mi sono alzato e ho entrato lì in basso.
E le genti che passeranno, oh bella ciao, bella ciao, bella ciao, 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 delle genti che passeranno, mi diranno che...
Una mattina mi sono alzato, bella ciao, bella ciao, bella ciao, ciao, ciao. Una mattina mi sono alzato e ho trovato il vaso.
again. You see
Ah, qual o problema? Não consegue ficar com a cabeça fora d'água? Sinta a ira do teu tridente. Ninguém escapa da minha fúria. Desista. Marés em ascensão, afoguem aqueles que se opõem a mim. Em frente, maré destruidora! Qual o problema?
To the rest. Come on. Do it. Do it! Do it. Do it. Do it. Do it. Do it! Who is doing it? Do it. Do it. All of it. Do it. Come on! Do it now!
Não consegue ficar com a cabeça fora d'água? Sinta a ira do teu tridente. Desista. Ninguém escapa da fúria. Em frente, maré destruidora. Adoro tirar onda com a sua cara. Ninguém escapa da minha fúria. Sinta a ira do teu tridente. Qual o problema? Não consegue ficar com a cabeça fora d'água? Ninguém escapa da minha fúria. Eu comi aquele repô no café da manhã e tomei alhos para ajudar a descer. Adoro tirar onda. Sua cara. scappa dal mio culo.
Okay. Testing 1, 2. Right battery charges coil. Right coil flies back into left battery. Left battery charges left coil. Left coil flies back into right battery. Right battery charges coil. Right coil flies back into left battery.
Qua un problema, non consegue fare questa testa con agua.
And the process repeats.
Io e torno a un mare.
The 2 coils over the 2 batteries are the same 2 coils positioned around the rotor 90 degrees. North magnets 180 degrees placed on the rotor facing north field out. Having them 180 degrees keeps your wheel balanced and also enables you to trigger 1 coil at a time because they're 90 degrees. You want to use transistors to trigger. You double pull the 2 gates over the battery, the 2 terminals, plus and minus terminal. Simultaneous trigger on them, open, off, together. You can use transistors, and you can put a trigger winding on the coil. Requires 2 transistors per source.
Her heart beating louder to confirm. Lying on the frozen lake, snowflake caught in her lashes. She was ready to let go.
I laid out this circuit on my channel, how to do that. Basically the same thing as the SG circuit, the way it triggers the transistor, only with, I think, an added diode to prevent unwanted triggering.
She was ready to let go.
Optimal is to use a high-speed relay so you don't have to worry about blowing a transistor. What's up, Raycar? Yeah, this first time I've heard this music. It probably is old, but good.
White powder blanket shielding her. Her heart beating louder to confirm. Lying on the frozen lake, snowflake caught in her lashes. She was ready to let go.
friends are heathens, take it slow. Wait for them to ask you who you know. Please don't let it go inside and know. You don't know what happened to you. All our friends are heathens, take it slow. Wait for them to ask you who you know. Please don't let it go inside and know. You don't know what happened to you.
I see what you mean by 100-year-old music
over and over and
updated.
over. But what you really want to do is you want to go as fast as you can without a capacitor, for the simple fact is...
So here, you know, this is showing how you wire the relay coil in series with the coils around the rotor.
You want to repeat this process over and over and over. But what you really want to do is you want to go as fast as you can without a capacitor, for the simple fact is you want to put a...
Before I play this video, I want to show the relay that you see in this cartoon edit that's really horribly drawn. I'm going to show you a version that's much clearer to see so you can see what's going on better on the other one. Be right back.
A lot of this radiant energy to the source.
Oh, right. That's White Bat Audio on YouTube. There's some good tracks. Royalty free. Let's go. Okay, this is the relay you see on the bottom left there.
Over and over and over.
Okay. So that's a clear shot of what the relay on the bottom left of this next video is doing. And I'll bring it up now. So, same relay. That's the same relay on the bottom left. You can see the two coils on top and bottom of the magnet. And take a moment to see how they're wired in series with the coils around the rotor. Having them in series enables you to position the drive coils around the rotor however you want. In this case, I needed them to be 90 degrees. Around the rotor. So this shows the series wiring of the relay coils with the drive coil attached to the relay terminals. The source batteries are on the left side of that relay, and the load to the coil are the bars on the right. You have four bars on the left, 4 bars on the right.
You want to repeat this process over and over and over. But what you really want to do is you want to go as fast as you can without a capacitor, for the simple fact is you want to put a lot of this radiant energy to the source.
better drawn out video of this relay, you know, I can show you the magnet actually moving instead of using arrows, which you saw previously. You can see the two batteries on the top left there. They represent the two pairs of bars on the relay on the bottom left. So the plus and minus comes in those bars from each battery. And you would hook your diodes, your high voltage 1N4007s, to those bars as shown in the you would hook them to the source bars. The source bars are to the left, the 4 bars on the left, plus and minus one source, plus and minus another source, 2 batteries. And those diodes would hook to the 2 diodes. One would hook to the plus bar, and the other diode would hook to the other plus bar, because the plus bar is the plus terminal on the battery, and the plus terminal on the battery is the left terminal. Okay, yeah, that's the relay. The same relay.
All my friends are heathens, take it slow. just to stay away. And now they're outside ready to buzz. It looks like you might be one of us. Why'd you come? You knew you should have stayed. I tried to warn you just to stay away. And now they're outside ready to buzz. It looks like you might be one of us.
Friends are heathens, take it slow.
Parametric excitation of oscillations.
Link is in the chat.
A fairground. Sometimes one can meet the good old swing boat. Swinging up and down, one can achieve surprisingly high amplitudes without the need to push oneself off the ground. This swinging is a special case of so-called parametric oscillations. How is such a parametric excitation possible? Let us watch, for simplicity, firstly the oscillation of a thread pendulum having the constant length L between its suspension point and the center of mass of the ball. It oscillates with a certain eigenfrequency, f0, which is given by the acceleration of free fall g and the length of the thread L. L and g are the so-called frequency-determining parameters. Without stimulating the pendulum to oscillations, at first the length L is varied periodically by means of the excenter, seen in the left part of the picture. Now the same periodic variation of L, but this time while the pendulum is oscillating. Increasing amplitudes are observed without any force acting in the direction of the oscillation. This means that this is not a forced oscillation. The length of the pendulum L, which in this case is varied, is the frequency determining parameter. This explains the name parametric oscillation. How are these increasing amplitudes of the oscillating pendulum produced? We can understand this by observing the forces working at different phases of the oscillation. Here, a pendulum of length L. During its oscillation, the ball is swinging on a part of an orbit. At the reversal points, the momentary velocity is equal to 0. Passing the center position, the ball has its maximum velocity. At this point, the force drawing at the thread is not only the full weight of the ball, Fs equals mg, but also the highest possible centrifugal force, Fz equals m omega head squared L. Omega head is the maximum angular velocity at the center position. At the reversal points, the centrifugal force equals 0 because the velocity is equal to 0. And besides this fact, along the thread, only the component of the weight mg cos alpha is acting. That means, at the reversal points, in total, a smaller force is drawing than at the center point. What happens when exciting the oscillations? While the pendulum is passing the center, its length is shortened. While going through the reversal points, it is lengthened. To recapitulate, what about the balance of energy? At the center point, we raise the ball against the here acting force for the distance 2 delta L, thereby putting in a certain amount of energy. In comparison, at the reversal points, we take out energy. But this energy is lower because the here acting force is smaller than at the center point. By this means, energy is pumped into the oscillating system. Let's watch once more the whole period. Obviously, in every period, there are 2 maxima and 2 minima of the acting force. Thus, we are able to supply energy to the oscillating pendulum 2 times per period. The maximum excitation is achieved if, firstly, the pump frequency Fp is the double of the eigenfrequency F0, and if, secondly, the feeding in of the energy always is done at the center point. In comparison, if we shift the phase of the excitation for half a period, now, we observe that, still with constant pump frequency, the amplitudes are decreasing. Being at rest at last, no variation of the thread length is able to produce new oscillations because in this state the energy supplied per period equals the energy taken out. Here the model of a swing boat. In this model, the distance between the suspension point and the center of gravity of the little man is the frequency determining parameter. A control circuit provides the correct pump frequency and correct phase. It does so by means of this excenter. For controlling the correct operating, namely the man straightening at this phase, suitable for supplying energy, the state of the oscillation is measured by a magnetic sensor. Pumping occurs with the double of the eigenfrequency. With optimum adaptation, very soon our model achieves large amplitudes. What happens if the pumping occurs with wrong phase adaptation? Switching over the control circuit has the effect that now the man straightens at the reversal points and crouches at the center point. As expected, now energy is removed from the system. The amplitude decreases. And when the swing is at rest, even prolonged pumping produces no observable amplitudes. Now we understand the role of the swingboat attendant. He has to make the swingboat swing before any energy supply is possible. This Foucault pendulum is oscillating in a fixed plane. Without external interference, it would shortly be standing still. By parametric excitation, it gets the proper energy for oscillating with constant amplitudes. This is the mechanism on the upper story. It raises and lowers the body of the pendulum with the correct pump frequency and the correct phase. The fact that parametric excitation is without influence on the plane of the oscillation is of special significance for the Foucault pendulum. The constant site of the plane of oscillation is known to be a presupposition for proving the rotation of the Earth, which can be observed by the fact that after 4 hours we can look at the plane of oscillation from another direction of view. Not only mechanical oscillations can be excited parametrically. Here, an electromagnetic oscillatory circuit consisting of an inductance L and a capacitance C. These parameters are responsible for the eigenfrequency F0 according to the formula of the mechanical pendulum. Let us observe a period of oscillation. For the starting state, we assume a maximum electrical charge on the capacitance. The capacitance discharges. And now it is empty. In turn, it is charged again, but with the opposite sign of the charge. Let us have a look at the inductance. A current is flowing, which now is highest, and then decreases to 0. With the current, a growing and vanishing magnetic field is combined. How can this system be supplied with energy? Let's do an experiment of thought. An iron core is pushed into the coil and is now pulled out. Pushing in is possible without any acting force, when no current flows and therefore no magnetic field exists. On the other hand, work is supplied to the coil by pulling the core out of the magnetic field while the current is flowing. In this way, the oscillating circuit gains energy. It functions parametrically because one of the parameters, namely the inductance L, is varied by moving the iron core in and out. In practice, of course, the inductance is not varied mechanically. Here, on the right-hand side, an oscillatory circuit with a capacitor and a coil on the blue core. A control winding left on the yellow core serves for exciting with the pump frequency Fp the circuit having the eigenfrequency F0. That's because a suitable current through the control winding varies the magnetic resistance and with it the inductance L of the circuit. Again, for the optimum case is valid Fp equals 2 F0. According to this scheme of electrical excitation, this so-called paraformer is constructed. On the left-hand side, the control winding, on the right, the oscillatory circuit. As an example for a suitable application, here a constant voltage circuit, an important part of which is the paraformer. Back to our oscillatory circuit, consisting of capacitance C and inductance L. We saw that by a suitable variation of L at the right moment, energy can be supplied. Equally, it should be possible to supply energy by variation of the capacitance C. What is the most feasible moment for inducing energy? Without any charges on the plates of the capacitor, no force is acting between them. When charged, the plates attract each other. So, one pulls the plates apart when they are charged and puts them together again in the discharged state. That means energy is supplied at the charged state, but no energy is removed at the discharged state. Obviously, again, the optimum pump frequency is 2 times the eigenfrequency of the circuit. In practice, the capacitance is not varied mechanically, but electrically. For example, by means of this semiconductor diode. It is much smaller than a pfennig coin. The value of its capacitance can be varied by the applied voltage. In this circuit, This so-called varactor diode is the most important part of a parametric high-frequency amplifier to which a pump voltage UP is applied. The oscillatory circuit is a resonant waveguide into which the varactor diode is incorporated on the right-hand side. Such amplifiers are used for receiving very weak signals from radio satellites. Remarkably, for this modern high-tech purpose, the same principle of parametric excitation is used as for the good old swing boat at the fairground.
While we're on transformers, there's one subject that I would like to bring up, and that's ferroresonance. There's very few people that have a good understanding of ferroresonance. Ferroresonance, let's see if I can spell this, ferroresonance, I hope I've got that right. Ferroresonance is a situation that can happen with transformers. I think with your understanding of basic electricity now and your work with transformers, this might be a good time to bring it up. Probably many of you have heard about it, and to a lot of people it's a phenomenon, hard to understand. With a good understanding of basic electricity, it really isn't that difficult. Basically, what happens in ferroresonance is that you destroy a transformer's ability to produce a counter-electromotive force. And in other words, even though it is an inductive load, instead of your current lagging by 90 degrees in that inductor or that high side winding of that transformer, what happens is you create a situation where instead of that inductor causing current to lag by 90 degrees, it comes in phase like it's a resistive load. That inductor, that high side winding of that transformer looks like a resistor. And of course, if it can't cancel the applied voltage, you see, then what happens? It just burns itself up. It's like putting DC on a transformer. It doesn't see a changing magnetic field, and so that the transformer looks at the winding like a resistance and it burns itself up. Probably the easiest way to describe what happens, that if I have an inductor and apply that to an alternating current circuit, and I'll draw a sine wave representing this alternating current. We know that if we have an inductor in that circuit, a purely inductive circuit now, that our current would lag by 90 degrees. In other words, my current in that particular circuit would look like this. If this was my applied voltage, this would be my current then in that inductor. It lags by 90 degrees. Now this current lagging by 90 degrees is also going to induce back on itself. So that when the alternating current makes its greatest rate of change is when you're going to get your greatest induced voltage. And that voltage is going to be equal and opposite in direction. Lenz's law states that. So that right here I'm making my greatest rate of change. Here's a peak and there's a peak. I'm making my greatest rate of change in my current at this point. That means that my induced voltage is going to be opposite than my applied voltage. It's going to be the greatest at that point. If I go through and then you see I'm making no rate of change here, it's going to be the least. If I would go through then and draw out my induced voltage that I would have back on itself, I'm going to have a voltage, a counter electromotive force or a back voltage that's going to be opposite the applied voltage. And then, of course, that's why you can tie a transformer, even though it's a continuous piece of wire in coil form. That's why you can apply it onto your circuit, your alternating current, and not burn it up. It's because it has that effect. In a purely inductive load, current lags by 90, it produces a counter electromotive force which cancels the applied voltage. So all you see when you energize that transformer is a little exciting current. That transformer is going to have some resistance, obviously. It can't be a purely inductive load. So you will see some arcing. Basically, it's a form of a regulator. You start drawing load off the low side, then you're changing the relationship of your current to your applied voltage, and you're going to start drawing more current on the high side. And so it's really a transformer is an amazing piece of equipment. Self-regulating device. Very, very low line losses and that sort of thing if you have a good, well-designed transformer. This represents a situation that would be normal. If, on the other hand, in my circuit, I created a situation where my current effect in that circuit would be to come in phase, then that load is going to look resistive. Now, a situation that would create this would be if I had a Y system. There's about 9 ways you can create this situation. Most common situation might be if I had a Y high side system and I have no ground. I'm floating my Y high side. And I have a situation that would apply a capacitance to that circuit. And if you'll remember, capacitance causes a current to lead. If I had the right amount of inductive and capacitive reactance, what's going to happen there is that the two would cancel one another out, and I would have my current in phase with my applied voltage. It would look like a resistive circuit. So that capacitive reactance of your transformer could be eliminated by capacitance added to that circuit. And you know from working with power factor what the effect is there. So when we say ferro, it's through the inductive, through the core side, from the low side, you can create a situation there where you can destroy that transformer. Resonant means in phase. That's where that comes from. So if you create a situation with your transformer bag where instead of the current in your inductor lagging by 90 degrees, it's because of capacitance on my circuit, it moves in phase with my applied voltage, then what's going to happen is you're going to destroy that transformer. It looks like a resistance, and you're going to have an excessive current flow and destroy that transformer. There are ways to eliminate that. Anything that would create a situation where you do not isolate that transformer with your capacitance. You can have it so that that circuit is out of. Give you an example. If I have a Y system, and I float this, and I lose one of my phases, say maybe a fuse blows here, and I've got a situation where I have no ground here, then what it'll do, it'll single phase out. And if I have a situation where in other words, these two transformers are going to move in line. Of course, this is what's going to happen. It's going to look like this. You're going to have a coil here. You're going to have your line, and here's your fuse. And say this fuse is blown, creating this single phasing situation. If I have a piece of underground cable applied to that, maybe I have a pad mount transformer up close to the building, then I go underground for a few feet over, and maybe maybe 100 feet over to, or 200 feet over to a pole, and then I have my fuses for that transformer on that pole. One of those fuses blows, I'm applying this capacitance of that underground cable onto that bank. Now, if I had grounded this out so that I didn't get a single phasing situation, you can cut down or eliminate the possibility that you would have ferro resonance from that, because this thing can open as an open Y situation, with this just removed from your circuit. There are various situations that can be created that will add to the problem. High voltage, small transformers, no load on the secondary side, all of those can contribute to more problems. We've had ferro resonance problems on overhead systems and probably didn't realize what it was. You do get some capacitance out of your overhead systems. You know, there's three variables that determine the value of capacitance. And of course, one is the size of the plates. If I had an overhead system and had long lines, very little inductive load in the form of transformers, regulators, or whatever, I can have a high capacitive effect. Another variable for capacitance is the distance between the plates. My spacing of my conductors on the pole or on the cross arm would determine the value of capacitive effect that I would get from that. Another variable, of course, is the dielectric material between them. Overhead system, you have air, and you'll remember that air is a dielectric constant of 1. We compare everything to air. Now, an underground cable is a very good capacitor. You have a section of underground cable, you see, your plates are right close to one another, adding to the capacitance. The length of your cable is going to be the size of your plates, and that also is a variable. And of course, you have a dielectric material between them, which is going to be much better than air. The dielectric constant, I don't know what a propylene would be, or cross-linked polyethylene. I'll back off. I'm not sure what the dielectric constant of that is, but it would be much better than air would be. So if you have underground cable, you can have a tremendous value of capacitive effect applied to your bank. You want to be aware of it. There are ways that you can get around it, or to cut down the possibility of having ferro resonance. And of course, one of them is to just ground out the high side of that bank instead of floating it. Now, I know what some of you are saying too. You want them floated. And the reason why you want to float them, particularly in a rural system, is that when you ground it out, it tries to regulate your system. If I have a Y delta bank, for example, and I ground that out, what happens if one of these phases tries to dip down, and I have this grounded, one of those phases tries to dip down, or maybe from a fault, or maybe more fully loaded, maybe you haven't got your system balanced up like it should be. What can happen with that anchored like that, that means two of these transformers are going to be anchored, and that means the value between any of the other two has to stay up there. Or two of the transformers will try and keep it there. If this phase tries to drop down, and here's the corresponding vector down here, if this was a high side, let's say a 7200, and let's say this is 240 volt. Let's say I've got this thing grounded, and this phase tries to drop down. Because this is in a fixed position from the other two transformers operating, you see, up above, that means that this wants to stay at 240 volt. If this tries to dip down, then what happens is that the other two transformers will try and sustain it. In other words, it'll act like a step-up transformer for that particular phase, adding an additional load onto that bank. So it tries to regulate the system when you ground it out. So that's why most rural systems that, at least till we get into underground, most rural systems, you always float it. Now there's problems if you float it. If you float it and say one of them drops off, then you can have ferro resonance. So you have unnecessary evil either way you go. But there's ways around that too. If you have to worry about ferro resonance on a circuit, or maybe you've had problems and haven't realized it, what you can do when you close your fuses in, when you close your fuses in on the bank, what's going to happen? You're going to close in, of course, one at a time. And what's going to happen? You close in one, if you had ferro resonance problem, now you close in one, you're going to notice much. You close in the second one, you're going to hear one whale of a buzz. And if you aren't quick enough to get the other one in, you may blow up a transformer from a situation which is ferro resonance. And I've heard of this happening on overhead systems more than once. What you can do to close it in is take that floated Y high side, that connection between your terminals on your high side, which is common. What you can do is take a ground set, treat it as though it's hot. Now, don't forget that. You can take that floated neutral, ground it out with a ground set, whatever the case might be, ground chain, whatever you call it. Then close in your phases, and then go back later and then remove it if you want to leave it floated. But you still have that possibility where if one fuse blows for any reason at all, you may destroy your transformers. So ferro resonance isn't that really difficult to understand. If you're ever asked, just say that you're creating a situation where a transformer does not have the possibility, or it does not create this counter electromotive force. So it doesn't have the possibility of canceling the applied voltage. The circuit looks resistive. It'd be like taking a coil. Say if I had a transformer here and I tied it onto alternating current, because of its inductive effect, I'm just going to see a small exciting current. If I would take that coil right there and straighten it out, what would happen? It no longer induces back on itself. It will look just like a resistor, and that's what happens in ferro resonance.
Hi friends, few of you have asked me to do a quick run through of the coil, and so we've got a beautiful Easter Sunday here in the Midwest, and I figured I'd just go over the basic functions and the components of my Tesla coil. I wanted to start over here first though and really quick show you the rings which I have been fabricating over the last month or so, and we'll hopefully go into the construction of a new torrid. That's basically 14 rings which are going to be joined to their equal counterpart, and that's a lot of work, but with luck that'll be done later this summer. Anyway, coming over here, the whole thing starts in this area. This is what I like to call the umbilical cord. It's a 240 volt fused dedicated outlet which comes out of the basement and is rated at 100 amps. Through this cable which winds around on the floor, coming over here to the first stop, the power variac. The power variac is rated at 20 kVA, and I'm inputting 240 volts. It is activated by two contactors, each of which taking one pole of the phase legs and making continuity to the transformer inside. From the variac, the next stop are the inductors. And I say inductors because I actually have an inductor bank which serves to choke the current on my coil, and it consists of 6 1,000 watt metal halide ballasts that have had the magnetic shunts knocked out of them. Each one of these 6 cells is submerged in a pot which is filled with mineral oil, and that oil is primarily used to insulate the inductors in the event that there's any short circuits or transient voltages which might work their way back up the system. From the inductors, the electricity is then fed into this big box, which I affectionately call the toy box. Inside of here are 6 small potential transformers, and those are wired in a series parallel configuration so that the output of that unit, when fed with 240 volts, will deliver 14.4 kV. Over here are the controls which are used to modulate the phasing on the synchronous spark gap, as well as provide a small voltage boost for the synchronous motor that I use in the Tesla coil. When I had originally upgraded my electrode size from 1/4 inch to 3/8 inch tungsten, the problem I encountered was that my synchronous motor was no longer strong enough or capable of spinning that tungsten rod at 3,600 RPM. As a consequence, it would fall out of synchronicity and the whole coil would go into asynchronous mode. That's bad. So I was able to secure a 50 hertz permanent magnet synchronous motor from a seller on eBay. The motor was originally used for applications designed for the military overseas. Getting to the long and short of it, what that enabled me to do, because the motor was rated at 50 hertz and I'm feeding it with 60 hertz, the reactance of the motor is slightly higher than what a 60 hertz motor would be. By applying an overvoltage of about 20%, I could get the necessary current to drive the motor at its rated torque. But because horsepower is a function of torque as well as speed or angular velocity, I was able to gain more horsepower because I'm spinning it at 3,600 RPM rather than 3,000 RPM. A long-winded explanation for something which really doesn't make sense to me, but it works and I'm happy about it, and we're going to move on. This is the phase controller, which is a modified variac, and it is turned into a variable inductor. In front of the phase controller is a small box which is filled with a number of capacitors. Those capacitors are used to counteract the inductive reactance of this variac, or this variable inductor, when we vary the phase. That provides resonance and voltage boost so that the voltage being supplied to the synchronous motor remains within an operational level. If we didn't have these, the minute we started to apply our inductance, we would see the phase fall back or out of synchronicity with the source that's feeding it, but we would also experience a significant voltage loss. That would be bad. So that's what this does. The way to figure out the amount of capacitance needed for this application is done through nothing but trial and error. Moving forward, this is my fancy pointer. It's a screwdriver. So Anyway, this is the cable that feeds the voltage source to the spark gap motor, the synchronous motor, which was that motor, if you remember that I said operates at, it's a 50 hertz motor that's operating at 60 hertz on an overvoltage of about 20%. That goes to the coil, and we'll walk down there in a minute and get to that. From the transformer box, or the toy box as I so affectionately call it, if you want to come over here, we have a set of high voltage cables, and these are electrically bonded to the output of the transformer bank. In its purest form, if I weren't to connect any load or reactive load of power on the other end of this, the voltage potential between these two insulators would be 14.4 thousand. Inside the tank circuit of the Tesla coil, I am utilizing an amount of capacitance which reacts with the inductors back at the beginning of this circuit, and because of that reaction through this transformer bank, we see a resonant rise voltage boost of almost twice as much electricity or voltage as what we started with. That essentially amounts to about 30,000 volts. That voltage is fed through these primary cables, or these high voltage cables, which are white, and it goes down to the body of the Tesla coil itself. Moving into the tank circuit of the Tesla coil, if you want to come and take a look at this, the control cable which was used to modulate the phasing or the positioning of the rotor on the motor is right here. That's plugged into this receptacle, and this cable itself is shielded and bonded with a braided ground that is not interconnected electrically to the powertrain back at the beginning of the circuit. That ground is bonded right here into this braided strap, which then exits the unit to either side into a grounding grid on either side, which I'll explain in a moment. The two high voltage primary cables, I call them primary because I associate high voltage with primary, being that I'm a lineman. I guess technically these would be secondary cables, but that to me makes no sense, so I'm going to call them primary, are connected to the spark gap, which is located right in here, and those two metallic balls are spaced at a distance of about 4/10 of an inch, about a centimeter, and that gives me a breakdown when the voltage between those two spheres exceeds about 28,000 volts, which is about where I want it. The motor, which is located back in there, and I can't reach in here because I have large ballistic plexiglass shields over this, is a propeller style. I'm not utilizing a disc style rotor. I found that with the type of motor I'm using, being that it is a true synchronous motor, and the fact that it worked so well within the framework of what it was designed to run at, the propeller gap was a much easier gap to fabricate, and I've had tremendous success with it. That is a 3/8 inch pure tungsten rod, 12 inches long. That motor spins at 3,600 RPM, which if you do the math means that the tip speed on that rotor, that tungsten rod, is somewhere around 137 to 140 miles an hour, give or take. That's off the top of my head. I may be in error about that, but I think it's fairly accurate. The two electrodes on either side of that tungsten rod are the short circuit electrodes that are used to channel the electricity into the primary coil up here when those capacitors in the back are charged. The whole tank circuit is wrapped in 1/2 inch plexiglass ballistic shielding. In case we were to have some sort of catastrophic failure in here, I wouldn't want the ejection of metallic parts moving at velocities of about 140 miles an hour. That would be bad. Tungsten happens to be very heavy. If you look at a periodic table, it's way down there at the bottom by uranium and plutonium and thallium and gold and lead and all that stuff. So we want to keep that stuff in here. Moving around to the back of the unit, the capacitors I'm using are the coveted Maxwell power caps, pulse discharge high voltage 40 kV. I have 3 cells in here. I don't remember specifically what each cell is rated at, but the total capacitance of this bank is 250 nanofarads. We have a break rate of 120 breaks per second. That's synchronous. That's what's called a slow break rate Tesla coil. And 250 nanofarads of capacitance is about as much as I can possibly cram into this thing without creating a wormhole. Remember, these capacitors are resonating to a certain extent with the inductors back at the beginning of the circuit through the coils of the transformer. When I originally designed the circuit, I had intended to use math as a way to figure out how to get about a 70 to 80% resonation rate between these two, and I found that the differential equations that were involved in calculating those numbers were absolutely impossible to solve with pen and paper. And you'd need MATLAB or something like that, which I don't know. So To try to numerically crunch the numbers on this like an engineer would do, it's just about impossible. To make matters even worse, you have a resonation that's occurring between the coils of a transformer bank, and those transformers have iron cores in them, and as you increase the current flowing through those transformers, you saturate the cores. So we have partial saturation of the cores of the transformer, which changes the reactance of those cores, and in so doing, it makes trying to figure out the relationship between these two specifically all but impossible. If you can do it, please let me know. I'd be happy to find out. Moving up, the primary coil is, I believe, 3/8 inch refrigerator tubing. We are tapped right now at 1, 2, 3, 4, 5, 7. Okay, 1, 2, 3, 4, 5, 6, 7 turns. And that's relatively low. That's a low tapping point for a Tesla coil, at least I think it is, but we're working with so much capacitance in the bottom of this thing that that's the tapping point necessary to create the resonance between the secondary circuit and the primary circuit. The secondary coil, or the form, is a 12-inch PVC tube ID. The outer diameter on that is 12.75 inches. I have about 1,200 turns of number 18 heavy build magnet wire, which is a coil length of somewhere around, I think, 50 to 52 inches. Don't remember off the top of my head, but it might be somewhere around there. It's about 28 ohms of wire resistance from the bottom to the top. That is wrapped in multiple layers of heavy duty, high voltage electrical tape. I did want to do the fancy dancy 20-something coats of polyurethane varnish on there and get a beautiful gold secondary form on this. I tried it. What I found out was that the power levels I was delivering to this coil were so high that any small miscalculation in the phasing or the frequency balance between the top and the bottom caused bad things to happen on this. And the only way to contain that type of electrical energy was to just wrap the heck out of this thing with thick electrical tape. That has, by and large, solved my problem. It may not be as aesthetically pleasing, but I'll tell you folks, when you run this thing at night and you've got this big black form here with the blue ultraviolet spark coming down, it actually looks very good because it does not reflect light, so it tends to make the whole surroundings a lot brighter, but I might be biased in that opinion. The Torrid is a standard HVAC flex tube. That's 14 inch. The outer diameter on that is approaching 60 inches. The center plate that I use to support that is made out of a, drum roll please, 30-inch pizza pan, if I remember correctly. Ordered off of Amazon, our good friends at Amazon. And like I said before at the beginning of this video, with luck, that ring Torrid in there will be finished by the middle of the summer. I hope I'm not jinxing myself, but that should add the final touch and a beautiful top piece and top load to this Tesla coil. Last point of interest that I wanted to make note of on this was the grounding system. The grounding system, I've taken extra steps and a large amount of effort to make sure that we have adequate grounding for this machine. I have two wires coming off and exiting to the sides of this coil. These wires are electrically connected to the strike rail, which is non-continuous around the top due to the fact that you don't want to get circulating currents in here when the coil is running. The makeshift Faraday cage that's created by the inclusion of these straps just is used to channel that electricity down into those ground wires. Those ground wires exiting off to either side, and this is a mirror image of the other side, are connected to a ground rod. That's an 8-foot ground rod driven to its maximum length. From this ground rod, we have two exiting wires underground, you can't see them, that go in either direction for a length of 12 feet, whereupon they are attached to two more ground rods. Those ground rods are 8 feet. We have the same thing on that side. So we have a total of 6 ground rods at 8 feet long for 48 feet in the ground. The ground is well sufficient to handle what it is that we're asking of it. All of these wires have been inserted or threaded through PVC clear tubing. The ground wires, the main power cable, the control cable, I found that that was necessary because during operation, those cables were drawing the attention of the streamers and the discharges from the top of the coil. It wasn't creating problems insofar as damaging things electrically, because all of these cables are high quality and they're shielded with a braid, but it was distracting from the intention that I wanted the coil to provide, which was to exit, go as far as possible, and then hit the ground. We're going to run tonight. With luck, we tried to run last night and we sheared a pin on the motor. That's since been replaced, thankfully. I am going to place a GoPro camera on the pavement in this vicinity. It'll be caged in a chicken wire, but the front will be open, and with luck, we will see the GoPro get hit by strikes, which should be a good effect. And if everything goes to plan, it should be a good show. Hope that does it.
It's all translations. So now we're going to expand on this thing. So here's the battery. Listen very closely here. That's the oscillators running in the machine. You see it wiggle? Now watch. That's because there's no output hooked up on it. So now what we want to do is we want to take this dead battery, and we'll get this thing to go here. See that it changed in tone? Now we're going to tell it to go. And we're going to watch over here. This was a completely dead battery, and you're going to see what's coming over here because now we have told it to charge the hell out of it, see? So see, it's up to 24 volts already. So this was a dead battery, so what we've done is we've increased these pulses now 8 times the amount. So what this battery is doing is charging itself up, and you can see that on the meter there. And so now as this battery starts to charge itself from a dead state, the impedance in the battery will drop down, and you'll get current in this battery. You'll be able to light a light here in a second. By the way, there is no RF used in this machine, but I want to show you that the energy in the primary battery is definitely there. And so if we were to just stop this for a second, we don't want to get our hands in there, and we put these lights in series. You don't see, remember we put this in series so that the energy has to flow through these lights to the battery. So now, if we look at the battery, See, the same voltage is there. So that means that the energy, and if you look at the lights very closely, as the battery changes impedance, the lights are starting to light. See, now let me take one of these off so we'll get it down to a level where you can see this. Just by disconnecting one bunch. See? Now this is over the top, this is 8 volts over the top of the battery. Okay, so you see, as this battery lowers its impedance, these lights will get brighter. Okay?
What's causing the impedance to be lower?
The energy that comes from the machine is trying to charge this dead battery, which is driving the sulfation off the plates. So now you're starting to return to a normal battery, see? So after charging this battery, okay, in the short time that we did, we should have some indication right now of current in this battery, and we do. The battery now has energy in it. See? Now, if you notice one thing, we didn't have this running all that long. Repeat this process over and over and over. But what you really want to do is you want to go as fast as you can without a capacitor, for the simple fact is you want to put a lot of this radiant energy to the source.